Well, students, we have completed the chapter on nonlinear equations. I hope you would have solved all the exercise problems that are given at the end of this chapter. In this lecture, we will pick up few of these problems and try to see how to solve them. Let us take the third problem. The problem says that we have to work with the bisection method to solve a nonlinear equation f of x equal to 0, starting with an initial interval a0 b0 with a0 greater than 0. So that is the key assumption that we have made in this problem. Now, as usual, we go on finding the xn's, which are precisely the midpoint of the interval an-1 to bn-1, right? Using the bisection method, and r is a root of the equation f of x equal to 0, to which our bisection method is converged. Now, given epsilon greater than 0, we would like to stop our iteration if the relative error becomes less than or equal to epsilon, right? So that is what we want. Now the question is, how many iterations are needed for us to perform in order to get the approximation xn such that r minus xn divided by r is less than or equal to epsilon. That is what we wanted to find. The number of iterations n. The problem says that you can show that n should be greater than or equal to log b minus a minus log epsilon. The epsilon is that tolerance that we have chosen, minus log a naught divided by log 2. The problem also asks us to think about what happens if this assumption is relaxed. Can we still get this inequality? That is the question. Well, log a is not defined. That itself is a clue that such an inequality should not be possible when a is less than 0. But still, we have to give the reasons behind why we cannot go for such inequality from a different point of view. Let us first see if a0 is greater than 0, how to get this inequality. Well, strictly speaking, it is not very difficult, because if you recall, as a part of the convergence theorem, we have proved some inequality. If you recall, as a part of the convergence theorem, we have shown that mod xn plus 1 minus r is less than or equal to 1 by 2 n plus 1 into b0 minus a0, right? So this is the absolute error estimate, but what we want now is the relative error estimate with respect to r. Therefore, clearly we have to divide both sides by r, right? Well, since a0 is greater than 0 and r lies between a0 and b0, therefore r should also be greater than 0. And in the class, as a corollary of this theorem, if you recall, we have obtained a similar inequality like this for n, right? What was the idea in deriving that inequality? We wanted the absolute error to be less than or equal to epsilon, and we had this inequality. Therefore, what we did there was that we imposed the condition that our right hand side is less than or equal to epsilon. Once you do that, obviously the leftmost will be less than or equal to epsilon. That is the idea. We can apply the same idea here also, that you take this part and try to see what is the corresponding n. Well, you should apply this inequality with n, not n plus 1. So you just replace this by n and then apply this inequality. And then you have to take log on both sides to get an estimate of n, right? But here the problem is this inequality involves r. right? R is the root of our nonlinear equation. Generally, we don't want to obtain any estimates that involves R because R is an unknown. Whereas any estimate that we would like to derive should be in such a way that the estimate that we obtain should be explicitly known to us. That is the main aim. If you try to get an estimate for n from this expression, then it will involve R, and R is unknown. So that is not good for us. So somehow we have to replace this R by some known quantity. How to do that? Well, it's a very simple idea, and that idea precisely use the fact that A naught is greater than 0. Okay, I leave it to you to think what is that simple elementary idea that is used in order to replace this R by a known quantity, that is precisely A naught. Once you do that appropriately, then you have to take log on both sides. And from there, you will get an estimate of n, which will be precisely this expression. That is how we have to prove the first part of this problem. Coming to the second part, well, you consider 3 cases. Case 1 is what happens when R is equal to 0. Well, in that case, the relative error is not well defined. Therefore, we have no hope for obtaining any estimate of this form, right? Next, take case 2 when R is strictly less than 0. Since A naught is less than or less than B naught, maybe less than or equal to, and R is less than 0, you may apply this elementary idea, but then you still this inequality will not go through very comfortably. You can see that. And therefore, even in this case, such an inequality is not possible. Now take case 3, where R is strictly greater than 0, in which case you will have A naught less than 0, less than or less than B naught. And in this case also, obviously, the inequality cannot go through because of the step where we try to eliminate R will not go through in this case also. Therefore, in all these 3 cases, we cannot obtain such an estimate for n when A naught is less than 0. So that you have to properly write these arguments and complete this problem. Next, let us take up the problem number 11. The problem asks us to discuss some instance where the secant method fails. If you recall, there are 2 instances where the secant method can fail. One instance is that when f of xn is equal to f of xn minus 1, then the secant method iteration xn plus 1 will become infinity. In that way, we can say that the iteration sequence is not well defined. The other instance where a secant method can fail is the case when the iterative sequence does not converge. You can graphically give some example for this. Consider the equation f of x equal to 0, where the graph of the function f looks like this, say. It asymptotically goes to 0 on this side, and it has some root here. And if you start your iteration with x naught somewhere here and x1 say somewhere here, then your x2 will be somewhere here, and x3 will be obtained by joining these 2 lines, and that will go here, x3, and so on. Your iteration will keep on going in this direction where you don't have any root, because the graph of the function f of x is asymptotical. It means it is going to 0, but it never intersects the x-axis at any finite x, right? In that way, we will never get a root of our equation, whereas the function f intersects the x-axis somewhere here, but you are actually going away from the root. In that way, your iterative sequence may diverge. Next, let us take up the problem number 16. Newton-Raphson method is to be applied for approximating a root of the equation sin x equal to 0. Write the formula for the Newton-Raphson iteration sequence. Generally, if we give a equation f of x equal to 0 and ask you to write the Newton-Raphson iteration sequence or any other for that matter like secant method or anything, you just have to substitute the function f of x into the formula of that iterative sequence and simplify it as much as possible. For instance, in this case, you have the iteration sequence for Newton-Raphson method is given by xn plus 1 is equal to xn minus f of xn divided by f dash of xn, right? Where f of x is given by sin x, right? So if you just write like this, that's not enough. You have to substitute the function f into the formula and simplify it. For instance, here, you have to also write xn plus 1 is equal to xn minus sin xn divided by cos xn. That can be in fact written as xn plus 1 is equal to xn minus tan xn, right? So finally, what we want as the answer for this question is this and not this. Okay, it is correct, but this is not enough for us to accept as the formula for the iterative sequence. So this is the complete formula for us. Okay, so the first part is therefore very easy to obtain. What is the second part of the question? The second part of the question says that you have to start with some number alpha in the interval minus pi by 2 to pi by 2. It's also given that alpha is not equal to 0. Be such that if I start my iteration, that is this iteration, with x naught is equal to that value, whatever alpha I should. What is meant by cycle? I told you in the class that if your iteration gets into a periodic move, like you start with x1 and get x2, like that, if you go at some level, say xm, you get back some of these values, say x3 for instance, then what happens is you just will keep on going. From x3 again you will get x4, x5, x6, like that xm. Once you touch xm, again it will jump back to x3 and you will be in this cycle, right? So you will keep on going like this. So that is what is called the cycle. In any iterative sequence it might happen. Now what the question asks is, you provide me a x naught such that I start with x naught, I will get x1 using this formula, right? Then I will get x2 by using x1 in this formula, but that x2 will be the same as x naught. And that, if you remember, we have taken it as alpha, right? Therefore, what will be x3? From x2, you will be computing x3. That will be the same as x1, right? Because x2 is same as x naught. Therefore, x3 will be same as x1. Therefore, x4, now keeping x3, which is same as x1, if you compute x4, then that will be same as x2. Like that, it will keep on going, right? You will never converge with this sequence. That is the problem. It is one of the pitfalls of any iterative sequence, especially for open domain methods. We can stuck in a cycle like this. And in this particular equation, that is sin x equal to 0, you can find a x naught such that you may land up in such a cycle. Now, the problem is asking you to give a nonlinear equation, g of x equal to 0. Carefully understand, to find an equation, nonlinear equation, g of x equal to 0. It means you have to find the function g, not the fixed point iteration. This is something else. So you have a nonlinear equation g of x such that its root, that is, you solve this equation and get the root of this equation, which has a non-zero root in the interval minus pi by 2 to pi by 2. That's the fact which is given as a condition in the problem. It means there is such a alpha. You have to find this equation whose root is alpha. I hope you understand the problem. So what we want to find is, we have to find this function g such that this nonlinear equation has a root alpha. If you start your x naught for this iteration equal to that alpha, then you will get into a cycle of this structure. That is what is the problem demanding. Let us see how to find this equation g of x equal to 0, right? Now what we want is that x2 equal to x4 equal to and so on, all even terms of the sequence, all should be equal to x0, which we have taken as alpha, right? Now what you do is, you take any n which is an even integer, then xn, that even integer, that is written as xn minus 1 minus tan xn minus 1, right? Remember, xn is equal to alpha. That is what is given to us here. Since n is even, that implies that alpha is equal to xn minus 1 minus tan xn minus 1. Okay. What is xn minus 1? Well, that contributes to an odd term that is not given to us, but only even terms are equal to alpha. But we know how this odd term xn minus 1 will look like. That will look like xn minus 2 minus tan xn minus 2, right? So this entire thing is just, I'm putting the formula for the iteration. Why I'm doing it? Because here I know that n minus 2 is an even term whenever xn is an even term, right? So that's the advantage of bringing this xn minus 1, which is an odd term, to an expression involving even term. Minus, similarly, tan, this is odd term. Again, you bring it to an expression in terms of even term by putting the formula for the term xn minus 1, which is given by, again, xn minus 2 minus tan xn minus 2, right? And that is equal to alpha, because this is equal to alpha, as xn minus 2 is an even term, minus tan alpha minus tan of alpha minus tan alpha, right? Now this is the nonlinear equation that you want, but you can further simplify it. So you just cancel this alpha with this alpha, and you have tan alpha is equal to minus tan alpha minus tan alpha, right? So that, of course, I can write as tan alpha minus alpha. That tells us that alpha satisfies this equation. Alpha is equal to tan alpha minus alpha, or tan alpha minus 2 alpha equal to 0. And that is your required nonlinear equation. That is, your g of x is given by tan x minus 2x. So 16th question also has 3 other subdivisions. These are just computational in nature. You can simply compute them and see. So I'll leave it to you to complete the other 3 parts of this problem. Next, let us consider the 25th problem. You have a sequence generated by a fixed point iteration method with a continuously differentiable iteration function g. If this sequence converges, then we have to show this inequality where lambda is the maximum of g dash of x in the interval ab. If you recall, this result is an important result because, if you recall, we have introduced some stopping criteria for an iterative sequence to be stopped when we reach the number of iterations in such a way that xn is pretty close to our root of interest, the value of the root, right? So for that, we remark that Cauchy criteria is a good criteria to be used as a stopping criteria. This inequality, in fact, justifies that. You can see on the right-hand side, it is the simplest form of the Cauchy criteria, and you can see that the absolute error involved in xn plus 1 when compared to the root of the equation can be made less than or equal to this quantity. And hence, if you make sure that the Cauchy criteria is satisfied, it means if you can make sure that this is less than or equal to, say, epsilon, then our mathematical error is automatically become less than or equal to epsilon, right? And hence our tolerance is reached. So in that way, this inequality is very important to justify that we can use Cauchy criteria as a valid stopping criteria. Let's see how to prove this inequality. We can write xn plus 1 minus x star as g of xn. Why? Because that is the way the fixed point iteration sequences are defined, minus g of x star. Why it is so? Because if your fixed point iteration sequence is converging, then the limit is a fixed point of your iteration function, right? Therefore, x star has to be equal to g of x star. Now take modulus on both sides and use the mean value theorem. You will get mod g dash of some xi n, where xi n lies between xn and x star, right? We have taken maximum of g dash to be lambda. Therefore, we can write this as less than or equal to lambda times mod xn minus x star, right? Now, let us take the right hand side. Mod xn minus x star can be written as mod xn minus xn plus 1 plus xn plus 1 minus x star, and that can be written less than or equal to mod xn minus xn plus 1 plus mod xn plus 1 minus x star, right? Triangle inequality. Substitute this into the above inequality. You will get xn plus 1 minus x star is less than or equal to lambda times mod xn minus xn plus 1 plus mod xn plus 1 minus x star. We are more or less done with what we want to show. You simply take this term to the left hand side. You'll see that 1 minus lambda times mod xn plus 1 minus x star is less than or equal to lambda times mod xn plus 1 minus xn, right? And that is precisely what we want to show. Xn plus 1 minus x star is less than or equal to lambda by 1 minus lambda. How can I bring 1 minus lambda to the other side without spoiling the inequality? Well, because we have to assume that lambda is less than 1. I'm sorry, I forgot to mention. Well, it's better to assume that lambda is less than 1. I think that should be there. Once you have that, then you can bring this, because then this will become positive term now, and therefore it can come to the other side and make it lambda by 1 minus lambda into mod xn plus 1 minus xn, right? So that's fine. So let us put one extra assumption here that lambda is less than 1. Let us take the problem number 24. You have a quadratic equation x square plus ax plus b equal to 0, whose roots are given by alpha and beta, both are real numbers, such that mod alpha is greater than mod beta. So this is also given to us. Now we are considering two iteration functions, g and h. Both of them satisfy the hypothesis of the convergence theorem of fixed point iteration method. That is, both G and H are self-map in their respective interval of definition. They both are continuously differentiable and they both are contraction maps. Now we are considering two iterative sequence generated by these two iteration functions. One is xn given by this expression and another one is yn given by this expression, and we have to show that xn converges to alpha and yn converges to beta. Since alpha and beta are roots of a quadratic equation, we have alpha plus beta is equal to minus a and alpha into beta is equal to b, right? Now from the way the iteration sequences are defined, we can see that g of x is equal to ax plus b by x and h of x is given by minus b by x plus a. Let us first take g of x. G satisfies all the hypotheses of the convergence theorem. Therefore, G is a self-map. G is continuous and continuously differentiable with G dash of x is less than 1 for all x in the interval in which it is defined and the self-map. But what is G dash? It is the derivative of ax plus b by x, and that is given by b by x square, and that is less than 1, and that implies mod b is less than x square, right? And this should hold for all n also. Therefore, for n equal to 0, 1, 2, and so on, we should have mod b less than xn square, right? Now, given that xn converges, let us assume that xn converges to x star. Since g is continuous, we will have x star is equal to g of x star. That is, x star is a fixed point of the function g, and also we will have b is less than x star square. But what is b? B is equal to alpha into beta. That implies mod alpha into mod beta is less than x star square. Remember, x star is either alpha or beta. Let us take x star as beta. Why? Because in this case, we want to show that xn is converging to alpha, right? It means we want to show in this case that x star is equal to alpha, but we will assume the contradiction that x star is beta and see that we arrive at a contradiction. How that is going to happen? Let us see. If you assume x star equal to beta, you just put it into this inequality. You will have mod alpha into mod beta is less than or equal to beta square, and that implies mod alpha is less than or equal to mod beta. Sorry, this is strictly less than, but what we assumed is mod alpha is strictly greater than mod beta. But we got just the opposite to what we assumed. Therefore, this cannot be the case, and that implies x star is equal to alpha. Now let us pass on to the next case, that is the sequence yn. Here the iterative sequence is defined as yn plus 1 equal to minus b by yn plus a. Therefore, h is defined as minus b by x plus a, right? That implies mod h dash of x is equal to mod b by x plus a the whole square. We have assumed that h satisfies all the hypotheses of the convergence theorem. Therefore, mod h dash of x has to be less than 1, and that implies mod b is less than x plus a whole square. That implies mod b is less than mod yn plus a, because this has to hold for each term of the iterative sequence yn, and also it holds for the limit x star, sorry, let us denote it by y star plus a the whole square, because we assume that yn converges to y star, and we have to show that y star is equal to beta. Now assume the contrary, that y star is equal to alpha, then we will have mod b is less than alpha plus a the whole square. But if you recall, we have alpha plus beta is equal to minus a. That implies alpha plus a is in fact equal to beta. Therefore, this implies mod b is less than beta square. But b is equal to alpha into beta. Therefore, mod alpha into mod beta is less than beta square. And that implies mod alpha is less than mod beta. Again, contradiction. Therefore, y star has to be equal to beta. So this completes the proof